The following is a conversation with Andrew Strominger, theoretical physicist at Harvard, whose research seeks to shed light on the unification of fundamental laws of nature, the origin of the universe, and the quantum structure of black holes and event horizons. And now, a quick few-second mention of each sponsor. Check them out in the description. It's the best way to support this podcast. We got 8 Sleep for naps, Rocket Money for saving on subscriptions, Indeed for hiring excellent teams, and ExpressVPN for security and privacy on the internet. Choose wisely, my friends. And now, onto the full ad reads. As always, no ads in the middle. I try to make this interesting, but if you skip them, please still check out our sponsors. I enjoy their stuff. Maybe you will too. And I should also mention that, as always, we're hiring folks to join our amazing team. And if you're interested or know somebody who might be interested, go to lexfriedman.com/hiring. This episode is brought to you by 8 Sleep and its new Pod 3 mattress. Today is actually an example of a day where it's been a pretty rough one. I didn't get much sleep the night before. I didn't get much sleep tonight. I had to do a bunch of really difficult work, especially programming work and then reviewing other people's code. I also had to record a podcast and also had to socialize, which is another kind of challenge altogether. And all of that combines to just this kind of mental state of maybe psychological, physical, all kinds of exhaustion. And it's kind of incredible how a short nap can fix so much of that. At least can fix the most important aspect, which is once you wake up, you see the world anew. That reinvigorated feeling of gratitude for being alive, for the beauty of the world, for being able to experience the beauty of the world. And a great nap, at least for me, does that just every single time. And in order to do a great nap, the best of the naps, you should do it on an 8 Sleep mattress. It keeps it cool, warm blanket, it's heaven. Check it out and get special savings when you go to 8sleep.com/Lex. This show is also brought to you by Rocket Money, a personal finance app that finds and cancels your unwanted subscriptions, monitors your spending, and helps you lower your bills all in one place. It always cracks me up when people have something like a treadmill in their basement or in their apartment or wherever, and you could just tell that treadmill has not been used in months, if not years. And to me, for my life, I hate having that treadmill there because it's a kind of symbolic, visceral reminder of promises to yourself that you have broken. Anyway, subscriptions are kind of like that, except they also waste your money. It's like, I plan to do this thing. I plan to consume this product or this service or to do this kind of reading or to do this kind of thing on the internet or whatever the subscription is. And then you realize I'm actually not using that thing. So save the money by using Rocket Money. It's an easy service that helps you get rid of the unwanted subscriptions. Anyway, go to rocketmoney.com/Lex to cancel unwanted subscriptions and manage your money the easy way. That's rocketmoney.com/Lex. This show is also brought to you by Indeed, a hiring website. I should also mention that we're currently hiring. We're always hiring. We have an amazing team of human beings that I'm truly proud of. I'm truly happy to stand beside as we take on the challenges of creative work in this particular podcast and beyond. Basically capturing in video form interesting ideas, interesting people, interesting concepts, whether it's educational, whether it's beyond maybe educational, almost like exploring the human condition, whether that's podcasts or videos or all that kind of stuff. Anyway, it's an amazing team and we're always growing it. And to do so, you have to use the best tools for the job. Indeed, to me, is an incredible tool for hiring. They have all kinds of stuff, including Instant Match tool that helps you find quality candidates. That's the first step, the hardest step, and to do that fast is super cool. Indeed knows when you're growing your own business, every dollar counts. That's why with Indeed, you only pay for quality applications that match your job requirements. Visit Indeed.com/Lex to start hiring now. That's Indeed.com/Lex. Terms and conditions apply. This show is also brought to you by ExpressVPN. I've used them for many years with a big red sexy button that I would press. And like Alice in Wonderland, escape into a world where nobody knows exactly where I am, but everybody is happy I'm there. And that's useful for like Netflix for watching content that's geographically restricted. But it's also useful in the way that the journey that Alice takes in Wonderland is useful because it allows you to do all kinds of stuff on the internet where your privacy is sensitive. I mean, everybody should be using a VPN, and maybe I'm biased, but I don't think so. I think ExpressVPN is the best, and you should use it. It works on any device. Again, I'm biased, but the best operating system, Linux, it works on that. But it works on your iPhone, Android. It works on Windows and Mac, everything, everywhere. And I should also mention it's super fast on those operating systems too. Anyway, go to expressvpn.com/LexPod for an extra 3 months free. This is the Lex Friedman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Andrew Strominger. You are part of the Harvard Black Hole Initiative, which has theoretical physicists, experimentalists, and even philosophers. So let me ask the big question. What is a black hole from a theoretical, from an experimental, maybe even from a philosophical perspective?
So a black hole is defined theoretically as a region of space-time from which light can never escape. Therefore, it's black. Now, that's just the starting point. Many weird things follow from that basic definition, but that is the basic definition.
What is light? That can't escape from a black hole.
Well, light is, the stuff that comes out of the sun, that stuff that goes into your eyes. Light is one of the stuff that disappears when the lights go off. The stuff that appears when the lights come on.
Yeah.
Of course, I could give you a mathematical definition, but or physical mathematical definition, but I think it's something that we will understand very intuitively. What is light? Black holes, on the other hand, we don't understand intuitively. They're very weird. And one of the questions is about black holes, which I think you were alluding to, is, why doesn't light get out? Or how is it that there can be a region of space-time from which light can't escape? It definitely happens. We've seen those regions. We have spectacular pictures, especially in the last several years, of those regions. They're there. In fact, they're up in the sky, thousands or millions of them. We don't yet know how many. But the proper explanation of why light doesn't escape from a black hole is still a matter of some debate. And one explanation, which perhaps Einstein might have given, is that light carries energy. It carries energy because, we have photocells and we can take the light from the sun and collect it, turn it into electricity. So there's energy in light. And anything that carries energy is subject to a gravitational pull. Gravity will pull at anything with energy. Now, it turns out that the gravitational pull exerted by an object is proportional to its mass. And so if you get enough mass in a small enough region, you can prevent light from escaping. And let me flesh that out a little more. If you're on the Earth and you're on a rocket ship leaving the surface of the Earth, and if we ignore the friction from the air, if your rocket accelerates up to 11 kilometers per second, that's escape velocity. And it can, if there were no friction, it could just continue forever to the next galaxy. On the moon, which has less mass, it's only 7 kilometers per second. So, but going in the other direction, if you have enough mass in one place, the escape velocity can become the speed of light. Mm-hmm. If you shine light straight up away from the Earth, it doesn't have too much trouble. It's going way above the escape velocity. And, but if you have enough mass there, even light can't escape the escape velocity. And according to Einstein's theory of relativity, there is an absolute speed limit in the universe, the speed of light, and nothing makes any sense. Nothing could be self-consistent if there were objects that could exceed light speed. And so in these very, very massive regions of space-time, even light cannot escape.
And the interesting thing is Einstein himself didn't think that these objects we call the black holes could exist. But let me actually linger on this.
Yeah, that's incredibly interesting. Yeah.
There's a lot of interesting things here. First, with the speed limit. How wild is it to you, if you put yourself in the mind in the time of Einstein before him, to come up with a speed limit of that there is a speed limit, and that speed limit is the speed of light? How difficult of an idea is that? Isn't it? You said from a mathematical physics perspective, everything just kind of falls into place, but he wasn't perhaps maybe initially had the luxury to think mathematically. He had to come up with it intuitively. Yes. So how counterintuitive is this notion to you?
Well,
is it still crazy?
No. So it's a very funny thing in physics. The best discoveries seem completely obvious in retrospect.
Yeah.
Even my own discoveries, which of course are far lesser than Einstein's, but many of my papers, many of my collaborators get all confused. We'll try to understand something. We say, we've got to solve this problem. We'll get all confused. Finally, we'll solve it. We'll get it all together. And then all of a sudden, everything will fall into place. We'll explain it. And then we'll look back at our discussions for the preceding months and literally be unable to reconstruct how confused we were.
Yeah.
And how we could ever have thought of it any other way.
That's so fascinating.
And so not only can I not fathom how confused Einstein was before when he started thinking about the issues, I can't even reconstruct my own confusion from 2 weeks ago. So the really beautiful ideas in physics have this very hard to get yourself back into the mindset. Of course, Einstein was confused about many, many things. It doesn't matter if you're a physicist. It's not how many things you got wrong. It's not the ratio of how many you got wrong to how many you got right. It's the number that you got right. So Einstein didn't believe black holes existed, even though he predicted them. And I went and I read that paper, which he wrote. Einstein wrote down his field equations in 1915, and Schwarzschild solved them and discovered the black hole solution 3 or 4 months later, in very early 1916. And 25 years later, Einstein wrote a paper. So with 25 years to think about what this solution means, wrote a paper in which he said that black holes didn't exist. And I'm like, well, if one of my students in my general relativity course wrote this, I wouldn't pass them.
You get a C minus. Oh, you wouldn't pass them. Okay. All right.
Get a C minus. Okay. Same thing with gravity waves. He didn't believe.
Oh, he didn't believe in gravitational waves either?
He went back and forth, but he wrote a paper in, I think, 34, saying that gravity waves didn't exist because people were very confused about what a coordinate transformation is. And in fact, this confusion about what a coordinate transformation is has persisted, and we actually think we're on the edge of solving it 100 years later.
Well,
100 years later.
What is coordinate transformation as it was 100 years ago to today?
Let's imagine I want to draw a map with pictures of all the states and the mountains, and then I want to draw the weather forecast, what the temperatures are going to be all over the country. Mm-hmm. And I do that using one set of weather stations, and I number the weather stations, and you have some other set of weather stations, and you do the same thing. So the coordinates are the locations of the weather stations.
Yeah.
They're how we describe where the things are. At the end of the day, we should draw the same map. That is coordinate invariance. And if we're telling somebody, we're going to tell somebody at a real physical operation, we want you to stay as dry as possible on your drive from here to California, we should give them exactly the same route. No
Sure.
matter which weather stations we use or how we, mm-hmm. It's a very trivial, it's the labeling of points is an artifact and not in the real physics.
Sure.
So it turns out that that's almost true, but not quite. There's some subtleties to it.
The statement that you should always have the same, give at least the same kind of trajectory, the same kind of instructions, no matter the weather stations.
Yeah. There's some very delicate subtleties to that, which began to be noticed in the 50s. It's mostly true, but when you have a space-time with edges, it gets very tricky how you label the edges.
And space-time in terms of space or in terms of time, in terms of everything, just space-time?
Either one. Okay. Space or time. That gets very tricky. And Einstein didn't have it right. And in fact, he had an earlier version of general relativity in 1914, which he was very excited about, which was wrong. It wasn't fully coordinate invariant. It was only partially coordinate invariant. It was wrong. It gave the wrong answer for bending light to the sun by a factor of 2. There was an expedition sent out to measure it during World War I. They were captured before they could measure it. And that gave Einstein 4 more years to clean his act up, by which time he'd gotten it right. So it's a very tricky business, but once it's all laid out, it seems it's clear.
Then why do you think Einstein didn't believe his own equations and didn't think that black holes are real? Well, why was that such a difficult idea for him?
Well, something very interesting happens in Schwarzschild solution of the Einstein equation. I think his reasoning was ultimately wrong, but let me explain to you what it was. At the center of the black hole, behind the horizon, in a region that nobody can see and live to tell about it, at the center of the black hole, there's a singularity, and if you pass the horizon, you go into the singularity, you get crushed, and that's the end of everything. Now, the word singularity means that it just means that Einstein's equations break down. They become infinite. You write them down, you put them on the computer. When the computer hits that singularity, it crashes. Everything becomes infinite. There's two. So the equations are just no good there.
Mm-hmm.
Now, that's actually not a bad thing. It's a really good thing. And let me explain why. So it's an odd thing that Maxwell's theory and Newton's theory never exhibit this phenomena. You write them down, you can solve them exactly. They're really Newton's theory of gravity. They're really very simple theories. You can solve them. Well, you can't solve the three-body problem, but you can certainly solve a lot of things about them. Nevertheless, there was never any reason, even though Maxwell and Newton perhaps fell for this trap, there were never any reason to think that these equations were exact. And there's no equation. Well, there's some equations that we've written down that we still think are exact. Some people still think are exact. My view is that there's no exact equation.
Everything is an approximation.
Everything is an approximation.
And you're trying to get as close as possible.
Yeah.
So you're saying objective truth doesn't exist in this world? The internet's going to be very mad at you.
We could discuss that, but that's a different thing. We wouldn't say Newton's theory was wrong. It had very, very small corrections, incredibly small corrections. It's actually a puzzle why they're so small. So if you watch the precession of Mercury's perihelion, this was the first indication of something going wrong. According to Newton's theory, Mercury has an elliptical orbit. The long part of it moves around as other planets come by and perturb it and so on. And so this was measured by Leverrier in 1859, and he compared theory and experiment, and he found out that the perihelion precess moves around the sun once every 233 centuries instead of every 231 centuries. Okay, now, this is the wonderful thing about science. Why was this guy? I mean, you don't have any idea how much work this is, But, of course, he made one of the greatest discoveries in the history of science without, even knowing what good it was going to be.
Mm-hmm.
So that's how small, that was the first sign that there was something wrong with Newton.
Yeah.
Now, so the corrections to Newton's law are very, very small, but they're definitely there. The corrections to electromagnetism, they're mostly, the ones that we see are mostly coming from quantum effects. And
so the corrections are for Maxwell's equations is when you get super tiny, and then the corrections for the for Newton's laws of gravity is when you get super big. That's when you require corrections.
That's true, but I would phrase it as saying when it's super accurate. If you look at the Bohr atom, Maxwell electromagnetism is not a very good approximation to the force between the proton and the electron. The quantum mechanics, if you didn't have quantum mechanics, the electron would spiral into the proton and the atom would collapse. It's quantum, so that's a huge correction there.
Sure.
So every theory gets corrected as we learn more. There'd just be no reason to suppose that it should be otherwise.
Well, how does this relate to the singularity? Why the singularity?
So when you hit the singularity, you know that you need some improvement to Einstein's theory of gravity. And that improvement, we understand what kind of things that improvement should involve.
Mm-hmm.
It should involve quantum mechanics. Quantum effects become important there. It's a small thing. And we don't understand exactly what the theory is, but we know there's no reason to think, Einstein's theory was invented to describe weakly curved things, the solar system, and so on. It's incredibly robust that we now see that it works very well near the horizons of around black holes and so on. So it's a good thing that the theory drives itself, that it predicts its own demise. Newton's gravity had its demise. There were regimes in which it wasn't valid.
Mm-hmm.
Maxwell's electromagnetism had its demise. There was regimes in which quantum effects greatly modified the equations. But general relativity, all on its own, drove a system which originally was fine, would perversely wander off into a configuration in which Einstein's equations no longer applied.
So to you, the edges of the theory are wonderful. The failures of the
edges are wonderful because that keeps us in business.
So that one of the things you said, I think, in your TED talk, that the fact that quantum mechanics and relativity don't describe everything, and then they clash, is wonderful. I forget the adjective you used, but it was something like this. So why is that? Why is that interesting? Do you in that same way that there's contradictions that create discovery?
There's no question in my mind. Yeah. Of course, many people would disagree with me, that now is the most wonderful time to be a physicist.
Why is that?
So people look back at it's a classical thing to say among physicists, I wish it were 1920.
Right.
Quantum mechanics had been just understood. There was the periodic table. But in fact, that was such a rich thing so that what a lot of exciting stuff happened around 1920. It took a whole century to sort out the new insights that we got,
especially adding some experimental stuff into the bunch, actually making observations and integrating all the
experimental thing.
All the computers also help with visualizations and all that kind of stuff.
Yeah. It was a whole sort of wonderful century. I mean, the seed of general relativity was the incompatibility of Maxwell's theory of the electromagnetic field with Newton's laws of gravity. They were incompatible because if you look at Maxwell's theory, there's a contradiction if anything goes faster than the speed of light. But Newton's theory of gravity, the gravitational field, the gravitational force, is instantaneously transmitted across the entire universe. So you could, if you had a friend on, in another galaxy with a very sensitive measuring device that could measure the gravitational field, they could just take this cup of coffee and move it up and down in Morse code, and they could get the message instantaneously over another galaxy. That leads to all kinds of contradictions. It's not self-consistent. It was exactly in resolving those contradictions that Einstein came up with the general theory of relativity. And it's fascinating how this contradiction, which seems like maybe it's kind of technical thing, led to a whole new vision of the universe. Now, let's not get fooled, because lots of contradictions are technical things. We haven't set up we run into other kinds of contradictions that are technical, and they don't seem to we understood something wrong. We made a mistake. We set up our equations in the wrong way. We didn't
Oh,
translate the formalisms.
as opposed to revealing some deep mystery that's yet to be
Yeah,
uncovered.
yeah. And so we're never very sure which are the really important ones.
But to you, the difference between quantum mechanics and general relativity the tension, the contradiction there seems to hint at some deeper thing that's going to be discovered in the century.
Yes, because that one has been understood since the 50s. Pauli was the first person to notice it, and Hawking in the early 70s gave it a really much more visceral form. And people have been hurling themselves at it, trying to reduce it to some technicality, but nobody has succeeded. And the efforts to understand it have led to all kinds of interesting relations between quantum systems and applications to other fields and so on.
Well, let's actually jump around.
Okay.
So we'll return to black holes. I have a million questions there, but
Okay.
let's go into this unification, the battle against the contradictions and the tensions between the theories of physics. What is quantum gravity? Maybe what is the standard model of physics? What is quantum mechanics? What is general relativity? What's quantum gravity? What are all the different unification efforts?
Okay. So,
Again, 5 questions.
yeah, it's a theory that describes everything with astonishing accuracy. It's the most accurate theory in the history of human thought. Theory and experiment have been successfully compared to 16 decimal place. We have that stenciled on the door where I work. It's an amazing feat of the human mind. It describes the electromagnetic interaction, unifies the electromagnetic interaction with the so-called weak interaction, which you need some good tools to even view the weak interaction. And then there's the strong interaction, which binds the quarks into protons. And the forces between them are mediated by something called Yang-Mills theory, which is a beautiful mathematical generalization of electromagnetism, in which the analogs of the photons themselves carry charge. And so this, the final piece of this, of the standard model, everything in the standard model has been observed, its properties have been measured. The final particle to be observed was the Higgs particle, observed over a decade ago.
Well, Higgs is already a decade ago.
I think it is, yeah.
Wow, time flies.
But you better check me on that. Yeah,
that's true. But so much fun has been happening.
So much fun has been happening, and so that's all. That's all pretty well understood. There are some things that might or might not around the edges of that. Dark matter, neutrino masses, some sort of fine points or things we haven't quite measured perfectly and so on, but it's largely a very complete theory, and we don't expect anything very new conceptually in the completion of that.
Anything contradictory by new? Because
anything contradictory? Yeah.
I'll have some wild questions for you on that front. But yeah, anything that because there's no gaps. It's so accurate, so precise in its predictions. It's hard to imagine something.
Yeah. And it was all based on something called let me not explain what it is. Let me just throw out the buzzword: renormalizable quantum field theory. They all fall in the category of renormalizable quantum field theory.
I'm going to throw that at a bar later to impress the girls.
Good luck.
Thank you.
Uh,
All right. So,
they all fall under that rubric.
mhm.
Gravity will not put that suit on. So the force of gravity cannot be tamed by the same renormalizable quantum field theory to which all the other forces so eagerly submitted.
What is the effort of quantum gravity? What are the different efforts to have these two dance together effectively to try to unify the standard model and general relativity, any kind of model of gravity?
Sort of the one fully consistent model that we have that reconciles that sort of tames gravity and reconciles it with quantum mechanics is string theory and its cousins. And we don't know what, or if in any sense, string theory describes the world, the physical world, but we do know that it is a consistent reconciliation of quantum mechanics and general relativity, and moreover, one which is able to incorporate particles and forces like the ones we see around us. So it hasn't been ruled out as an actual sort of unified theory of nature, but there also isn't in my view, some people would disagree with me, but there isn't a reasonable possibility that we would be able to do an experiment in the foreseeable future, which would be sort of a yes or no to string theory.
Okay, so you've been there from the early days of string theory. You've
Right.
seen its developments. What are some interesting developments? What do you see as also the future of string theory? And what is string theory?
Well, the basic idea which emerged in the early 70s was that if you take the notion of a particle and you literally replace it by a little loop of string, that strings are sort of softer than particles.
What do you mean by softer?
Well, if you hit a particle, if there were a particle on this table, a big one, and you hit it,
Yeah.
you might bruise yourself.
Sure.
But if there was a string on the table, you would probably just push it around.
Mhm.
And the source of the infinities in quantum field theory is that when particles hit each other, it's a little bit of a jarring effect. And I've never described it this way before, but it's actually scientifically accurate. But if you throw strings at each other, it's a little more friendly. One thing I can't explain is how wonderfully precise the mathematics is that goes into describing string theory. We don't just wave our hands and throw strings around. And, there's some very compelling mathematical equations that describe it. Now, what was realized in the early 70s is that if you replace particles by strings, these infinities go away, and you get a consistent theory of gravity without the infinities. Mm-hmm. And that may sound a little trivial, but at that point, it had already been 15 years that people had been searching around for any kind of theory that could do this. And it was actually found kind of by accident. And there are a lot of accidental discoveries in this subject. Now, at the same time, it was believed then that string theory was an interesting sort of toy model for putting quantum mechanics and general relativity together on paper, but that it couldn't describe some of the very idiosyncratic phenomena that pertain to our own universe, in particular, the form of so-called parity violation. Our world is...
another term for the bar later tonight.
Yeah.
Parity violation. Okay.
So if you go to the bar and...
I already got the renormalizable quantum
and you
field
look
theory.
in the mirror across the bar,
Yes.
the universe that you see in the mirror is not identical. You would be able to tell if you show the lady in the bar a photograph that shows both the mirror and you.
There's a difference.
If she's smart enough, she'll be able to tell which one is the real world and which one is you. Now, she would have to do some very precise measurements. Yes. And if the photograph was too grainy, it might not be possible. But in principle, it's possible.
Why is this interesting? Does this mean that there's some not perfect determinism, or what does that mean? There's some uncertainty?
No, it's a very interesting feature of the real world that it isn't parity invariant. In string theory, it was thought could not tolerate that. And then it was learned in the mid-'80s that not only could it tolerate that, but if you did things in the right way, you could construct a world involving strings that reconciled quantum mechanics and general relativity, which looked more or less like the world that we live in. And now, that isn't to say that string theory predicted our world. It just meant that it was consistent, that the hypothesis that string theory describes our world can't be ruled out from the get-go. And it is also the only proposal for a complete theory that would describe our world. Still, nobody will believe it until there's some kind of direct experiment. And I don't even believe it myself.
Sure, which is a good place to be mentally as a physicist, right?
Yeah.
Always. I mean, Einstein didn't believe his own equations, right, with the black hole. Okay.
Well, that one he was wrong about that. He was wrong about that.
But you might be wrong too, right? So do you think string theory is dead if you were to bet all your money on the future of string theory?
I think it's a logical error to think that string theory is either right or wrong or dead or alive. What it is a stepping stone. And an analogy I like to draw is Yang-Mills theory, which I mentioned a few minutes ago in the context of standard model. Yang-Mills theory was discovered by Yang and Mills in the 50s, and they thought that the symmetry of Yang and Mills theory described the relationship between the proton and the neutron. That's why they invented it. That turned out to be completely wrong. It does, however, describe everything else in the standard model. And it had a kind of inevitability. They had some of the right pieces, but not the other ones.
Sure.
They didn't have it quite in the right context. And it had an inevitability to it, and it eventually sort of found its place. And it's also true of Einstein's theory of general relativity. He had the wrong version of it in 1914, and he was missing some pieces. And you wouldn't say that his early version was right or wrong. He'd understood the equivalence principle. He'd understood space-time curvature. He just didn't have everything. I mean, technically, you would have to say it was wrong. And technically, you would have to say Yang and Mills were wrong. And I guess in that sense, I would believe just odds are. We always keep finding new wrinkles. Odds are we're going to find new wrinkles in string theory. And technically, what we call string theory now isn't quite right, but
we're always going to be wrong, but hopefully a little bit less wrong every time.
Exactly. And I would, bet the farm, as they say.
Do you have a farm?
I say that much more seriously because not only do I have a farm, but we just renovated it. Before I renovated betting at the farm, my wife and I spent 5 years renovating it. Before
you were much looser with that statement, but now it really means something.
Now it really means something, and I would bet the farm on the guess that 100 years from now, string theory will be viewed as a stepping stone towards a greater understanding of nature. And it would, I mean, another thing that I didn't mention about string theory is, of course, we knew that it solved the infinities problem, and then we later learned that it also solved Hawking's puzzle about what's inside of a black hole. And you put in one assumption, you get 5 things out. Somehow you're doing something right. Mm-hmm. Probably not everything, but you're there's some good signposts, and there've been a lot of good signposts like that.
It is also a mathematical toolkit, and you've used it. You've used it with Kamran Vafa. Maybe we can sneak our way back from string theory into black holes. What was the idea that you and Kamran Vafa developed with the holographic principle in string theory? What were you able to discover through string theory about black holes, or that connects us back to the reality of black holes?
Yeah. So that is a very interesting story. I was interested in black holes before I was interested in string theory. I was sort of a reluctant string theorist in the beginning. I thought I had to learn it because people were talking about it. But, once I studied it, I grew to love it. First, I did it in a sort of dutiful way. These people say they've claimed quantum gravity. I ought to read their papers at least. And then the more I read them, the more interested I got. And I began to see, they phrased it in a very clumsy way. The description of string theory was very clumsy and
mathematically clumsy, or just
mathematically
the interpretation?
Clumsy.
Okay,
yeah, it was all correct, but mathematically clumsy. But it often happens that in all kinds of branches of physics that people start working on it really hard, and they sort of dream about it and live it and breathe it, and they begin to see inner relationships, and they see a beauty that is really there. They're not deceived. They're really seeing something that exists. But if you just kind of look at it, you can't grasp it all in the beginning. And so our understanding of string theory in 1985 was almost all about weakly coupled waves of strings colliding and so on. We didn't know how to describe a big thing like a black hole in string theory. Of course, we could show that strings in theory in some limit reproduced Einstein's theory of general relativity and corrected it, but we couldn't do any better with black holes than before my work with Kamran. We couldn't do any better than Einstein and Schwarzschild had done. Now, one of the puzzles, if you look at the Hawking's headstone and also Boltzmann's headstone, and you put them together, you get a formula for their really central equations in 20th century physics. I don't think there are many equations that made it to headstones. and they're really central equations, and you put them together and you get a formula for the number of gigabytes in a black hole. Now, in Schwarzschild's description, the black hole is literally a hole in space, and there's no place to store the gigabytes. And it's not too hard to, and this really was Wheeler and Bekenstein and Wheeler, Bekenstein, and Hawking to come to the conclusion that if there isn't a sense in which a black hole can store some large number of gigabytes, that quantum mechanics and gravity can't be consistent.
We got to go there a little bit. So how is it possible when we say gigabytes that there's some information? So black holes can store information. How is this thing that sucks up all light and is supposed to basically be, be super homogeneous and boring? How is that actually able to store information? Where does it store information? On the inside, on the surface?
Yeah.
Where's
Yeah.
and what's information? I'm liking this ask 5 questions to see which one you actually answer.
Oh, okay.
I'm
So
gonna
did you
ask you a
say
bunch
that
of.
I should try to memorize them and answer each one in order, just to answer
No,
them
I don't know.
now?
I don't know what I'm doing. I'm
Okay.
desperately trying to figure it out as we
Okay.
go along here.
So Einstein's black hole, the Schwarzschild black hole, they can't store information. Stuff goes in there and it just keeps flying and it goes in the singularity and it's gone. However, Einstein's theory is not exact. It has corrections. And string theory tells you what those corrections are. And so you should be able to find some alternate way of describing the black hole that enables you to understand where the gigabytes are stored. So what Hawking and Bekenstein really did was they showed that physics is inconsistent unless a black hole can store a number of gigabytes proportional to its area divided by 4 times Newton's constant times Planck's constant.
And that's another wild idea. You said area, not volume.
Exactly. And that's the holographic principle.
The universe is so weird.
And that's the holographic principle.
That's called the holographic principle. That it's the area. We're just jumping around. What is the holographic principle? What does that mean? Is there some kind of weird projection going on? What the heck?
Well, I was just before
about?
I came here writing an introduction to a paper, and the first sentence was the as yet imprecisely defined holographic principle. Blah, 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 blah.
Nice.
So nobody knows exactly what it is, but roughly speaking, it says just what we were alluding to, that really all the information that is in some volume of space-time can be stored on the boundary of that region.
So this is not just about black holes, it's about any area of space-time.
Any area of space. However, we've made sense of the holographic principle for black holes. We've made sense of the holographic principle for something which could be called anti-de Sitter space, which could be thought of as a black hole turned into a whole universe. And we don't really understand how to talk about the holographic principle for either flat space, which we appear to live in, or asymptotically de Sitter space, which the astronomers tell us we actually live in as the universe continues to expand. So it's one of the huge problems in physics is to apply or even formulate the holographic principle for more realistic. Well, black holes are realistic; we see them, but in more general context, to give a more general statement of the holographic principle.
What's the difference between flat space and asymptotic de Sitter space? So flat space is just an approximation of like the world we live in. So like de Sitter space, asymptotic. I wonder what that even means. Meaning like asymptotic over what?
Okay, so for thousands of years, until the last half of the 20th, until the 20th century, we thought space-time was flat.
Can you elaborate on flat? Like, what do we mean by flat?
Well, like the surface of this table is flat. Let me just give an intuitive explanation. Surface of the table is flat, but the surface of a basketball is curved. So the universe itself could be flat, like the surface of a table, or it could be curved like a basketball, which actually has a positive curvature. And then there's another kind of curvature called a negative curvature. And curvature can be even weirder because that kind of curvature I've just described is the curvature of space. But Einstein taught us that we really live in a space-time continuum, so we can have curvature in a way that mixes up space and time. And that's kind of hard to visualize.
Because you have to step, a couple of dimensions up. So it's hard to...
You have to step a couple, but even if you have flat space and it's expanding in time, we could imagine we're sitting here, this room, good approximation, it's flat, but imagine we suddenly start getting further and further apart. Then space is flat, but it's expanding, which means that space-time is curved.
Ultimately, it's about space-time. Okay, so what's de Sitter and anti-de Sitter space?
The three simplest spacetimes are flat spacetime, which we call Minkowski spacetime, and negatively curved spacetime, anti-de Sitter space, and positively curved spacetime, de Sitter space. And so astronomers think that on large scales, even though for thousands of years we hadn't noticed it, beginning with Hubble, we started to notice that space-time was curved. Space is expanding in time means that space-time is curved.
Mm-hmm.
And the nature of this curvature is affected by the matter in it, because matter itself causes the curvature of space-time. But as it expands, the matter gets more and more diluted. And one might ask, when it's all diluted away, is space-time still curved? And astronomers believe they've done precise enough measurements to determine this. And they believe that the answer is yes. The universe is now expanding. Eventually, all the matter in it will be expanded away, but it will continue to expand because, they would call it the dark energy. Einstein would call it a cosmological constant. In any case, in the far future, matter will be expanded away and we'll be left with empty de Sitter space.
Okay, so there's this Einstein's cosmological constant that now hides this thing that we don't understand called dark energy. What's dark energy? What's your best guess at what this thing is? Why do we think it's there? It's because it comes from the astronomers.
Dark energy is synonymous with positive cosmological constant. And we think it's there because the astronomers have told us it's there. And they know what they're doing.
And we don't know what the heck it is.
It's a really, really hard measurement, but they really know what they're doing. And we have no friggin' idea why it's there. Another big mystery. Another reason it's fun to be a physicist. And if it is there, why should it be so small? Why should there be so little? Why should it have hid itself from us? Why shouldn't there be enough of it to substantially curve the space between us and the moon? Why did there have to be such a small amount that only the crazy best astronomers in the world could find it?
Well, can't the same thing be said about all of the constants? Can't that be said about gravity? Can't that be said about the speed of light? Like, why is the speed of light so slow?
So fast.
So slow. Relative to the size of the universe, can't it be faster? Or no?
Well, the speed of light is a funny one because you could always choose units in which the speed of light is 1. We measure it in kilometers per second, and it's 100 86,000 or miles per second is 186,000 miles per second. But if we had used different units,
Yeah.
then we could make it one. But you can make dimensionless ratios. So, you could say, why is the time scale set by the expansion of the universe so large compared to the time scale of a human life, or so large compared to the time scale for a neutron to decay?
Yes. Yeah. I mean, ultimately, the temporal reference frame here is a human life.
Maybe.
Isn't that the important thing for us, descendants of apes? Isn't that a really important aspect of physics? Like, because we kind of experience the world, we intuit the world through the eyes of these biological organisms.
Absolutely.
I mean, I guess mathematics helps you escape that for a time, but ultimately, isn't that how you wonder about the world?
Absolutely.
That like a human life times only 100 years. Because if you think of everything, if you're able to think in, I don't know, in billions of years, then maybe everything looks way different. Maybe universes are born and die, and maybe all of these physical phenomena become much more intuitive that we see at the grand scale of general relativity.
Well, that is one of the, a little off the track here, but that certainly is one of the nice things about being a physicist is you spend a lot of time thinking about, insides of black holes and billions of years in the future. And it sort of gets you away from the day-to-day into another fantastic realm. But I was answering your question about how there could be information in a black hole.
Yes.
So Einstein only gave us an approximate description, and we now have a theory that corrects it, string theory. And now sort of was the moment of truth. Well, when we first discovered string theory, we knew from the get-go that string theory would correct what Einstein said, just like Einstein corrected what Newton said. But we didn't understand it well enough to actually compute the correction, to compute how many gigabytes there were. And sometime in the early 90s, we began to understand the mathematics of string theory better and better. And it came to the point where it was clear that this was something we might be able to compute. And it was a kind of moment of truth for string theory, because if it hadn't given the answer that Bekenstein and Hawking said it had to give for consistency, string theory itself would have been inconsistent and we wouldn't be doing this interview.
Mm-hmm. Wow. That's a very dramatic statement. But yes.
That's not the most dramatic thing.
I mean, but okay, that's very life and death. You mean like that because string theory was central to your work at that time? Is that what you mean?
Well, string theory would have been inconsistent.
Yeah, okay. So then
string theory would have been inconsistent.
But those inconsistencies can give birth to other theories, like you said.
The inconsistency, right? Something else could have happened.
Yes.
Yeah, it would have been a major change in the way we think about string theory and it was a good thing that, one supposition that the world is made of strings solves two problems, not one. It solves the infinity problem and it solved the Hawking's problem. And also the way that it did it was very beautiful. It gave an alternate description. So alternate description of things are very common. I mean, to take a simple example, this bottle of water here is 90% full. I could say it's 90% full. I could also say it's 10% empty. Those are obviously the same statement. And it's trivial to see that they're the same, but there are many statements that can be made in mathematics and mathematical physics that are equivalent, but might take years to understand that they're equivalent, and might take the invention or discovery of whole new fields of mathematics to prove they're equivalent. And this was one of those. We found an alternate description of certain black holes in string theory, which we could prove was equivalent. And it was a description of the black hole as a hologram that can be thought of, a holographic plate that could be thought of as sitting on the surface of the black hole, and the interior of the black hole itself sort of arises as a projection, or the near horizon region of the black hole arises as a projection of that holographic plate. So the two descriptions were the hologram, the three-dimensional image, and the holographic plate. And the hologram is what Einstein discovered, and the holographic plate is what we discovered. And this idea that you could describe things very, very concretely in string theory in these two different languages, of course, took off and was applied to many different contexts within string theory.
So you mentioned the infinity problem and the Hawking problem. Which Hawking problem? That the black hole destroys information, or which Hawking problem are we talking about?
Well, there's really two Hawking problems. They're very closely related. One is, how does the black hole store the information?
Yes.
And that is the one that we solved in some cases. So it's sort of like, your smartphone. How does it store its 64 gigabytes? Well, you rip the cover off and you count the chips, and there's 64 of them, each with a gigabyte, and there's 64 gigabytes. But that does not solve the problem of how you get information in and out of your smartphone. You have to understand a lot more about the Wi-Fi and the internet and the cellular, and
that's where Hawking radiation, this prediction, starts to.
That's where Hawking radiation comes in, and that problem of how the information gets in and out. You couldn't have explained how information gets in and out of an iPhone without first explaining how it's stored in the first place.
Yeah. So just to clarify, the storage is on the plate,
on the plate,
on the holographic plate, and then it projects somehow inside the
bulk, the space-time is the hologram.
The hologram. But man, I mean, do you have an intuitive, when you sit late at night and you stare out at the stars, do you have an intuitive understanding of what a holographic plate is? Like that there's two-dimensional projections that store information?
How a black hole could store information on a holographic plate, I think we do understand in great mathematical detail, and also intuitively. And it's very much like an ordinary hologram, where you have a holographic plate and it contains all the information. You shine a light through it, and you get an image which looks three-dimensional.
Yeah, but why should there be a holographic plate? Like,
why should there be?
Yeah, why?
That is the great thing about being a theoretical physicist, is anybody can very quickly stump you with going to the next level of whys.
Yeah, like,
so if you're asking,
I can just keep asking. Yes.
Yeah, you could just keep asking, and it won't take you very long to. So the trick in being a theoretical physics is finding the questions that you can answer.
Sure.
So the questions that we think we might be able to answer now, and we've partially answered, is that there is a holographic explanation for certain kinds of things in string theory.
Sure.
We've answered that. Now we'd like to take what we've learned, and that's what I've mostly been doing for the last 15, 20 years. I haven't really been working so much on string theory proper. I've been sort of taking the lessons that we learned in string theory and trying to apply them to the real world assuming only what we know for sure about the real world.
So on this topic, you co-authored a paper with Stephen Hawking called "Soft Hair on Black Holes."
Yes.
That makes the argument against Hawking's original prediction that black holes destroy information. Can you explain this paper?
Yes.
And the title.
Okay. So first of all, the hair on black holes is a word that was coined by the greatest phrase master in the history of physics, John Wheeler, invented the word black hole.
Mm-hmm.
And he also said that he made the statement that black holes have no hair.
Mm-hmm.
That is, every black hole in the universe is described just by its mass and spin. They can also rotate, as was later shown by Kerr. Mm-hmm. And this is very much unlike a star, right? Every star of the same mass is different in a multitude of different ways. Different chemical compositions, different motions of the individual molecules. Every star in the universe, even of the same mass, is different in many, many different ways. Black holes are all the same. And that means when you throw in Einstein's description of them, which we think must be corrected. And if you throw something into a black hole, it gets sucked in. And if you throw in a red book or a blue book, the black hole gets a little bigger, but there's no way within Einstein's theory of telling how they're different. And that was one of the assumptions that Hawking made in his 1974-75 papers, in which he concluded that black holes destroy information. You can throw encyclopedias, thesis defenses, the Library of Congress.
It doesn't matter. It's going to behave exactly the same uniform way.
Yeah. So what Hawking and I showed, and also Malcolm Perry, is that one has to be very careful about what happens at the boundary of the black hole. And this gets back to something I mentioned earlier about when two things which are related by a coordinate transformation are and are not equivalent. And what we showed is that they're very subtle imprints when you throw something into a black hole. There are very subtle imprints left on the horizon of the black hole, which you can read off at least partially what went in. And so this invalidates Stephen's original argument that the information is destroyed.
And that's the soft hair.
That's the soft hair, right. So, and soft is a word that is used in physics for things which have very low energy. And these things actually carry no energy. There are things in the universe which carry no energy.
You said, I think to Sean Carroll, by the way, everyone should go check out Sean Carroll's Mindscape podcast. It's incredible. And Sean Carroll's an incredible person. I think you said there, maybe in a paper, I have a quote. You said that a soft particle is a particle that has zero energy, just like you said now. And when the energy goes to zero, because the energy is proportional to the wavelength, it's also spread over an infinitely large distance. If you like, it's spread over the whole universe. It somehow runs off to the boundary. What we learned from that is that if you add a zero energy particle to the vacuum, you get a new state. And so there are infinitely many vacua, plural for vacuum,
right,
which can be thought of as being different from one another by the addition of soft photons or soft gravitons.
Right.
Can you elaborate on this wild idea? If you like, it spreads over the whole universe. When the energy goes to zero, because the energy is proportional to the wavelength, it also spreads over an infinitely large distance. If you like, it's spread over the whole universe. It's spread over the whole universe. What can you explain these soft gravitons and photons?
Yeah. So the soft gravitons and photons have been known about since the 60s, but exactly what we're supposed to do with them or how we're supposed to think about them, I think has been well understood only recently. And in quantum mechanics, the energy of a particle is proportional to Planck's constant times its wavelength. So when the energy goes to zero, the wavelength goes to infinity.
Mm-hmm.
Now, if something has zero energy and it's spread all over the universe, in what sense is it actually there? That's been the confusing thing. To make a precise statement about when something is and isn't there. Now, the simplest way of seeing, so people might have taken the point of view that if it has zero energy and is spread all over the universe, it's not there, we can ignore it. Mm-hmm. But if you do this, you'll get into trouble. And one of the ways that you'll get into trouble is that even though it has zero energy, it doesn't have zero angular momentum. If it's a photon, it always has angular momentum 1. If it's a graviton, it's angular momentum 2. So you can't say that the state of the system with the zero energy photon should be identified with the one without the zero energy photon, that we can just ignore them, because then you will conclude that angular momentum is not conserved. And if angular momentum is not conserved, things won't be consistent. And of course, you can have a lot of these things, and typically you do get a lot of them. And when you can actually do a calculation that shows that every time you scatter two particles, you create an infinite number of them.
Infinite number of the soft photons and gravitons?
Of the zero energy ones, yeah.
And so they're somehow everywhere. But
they're everywhere.
But they're also contain information, or they're able to store information?
And they're able to store information. They're able to store an arbitrary large amount of information. So what we pointed out is, so what these things really do, one way of thinking of them is they rush off to the edges of the universe, spreading out all over the space. Is like saying they rush off to the energy edge of the universe.
Right.
And that includes, if the interior of the black hole is not considered part of the universe, that includes the edge of the black hole. So we need to set up our description of physics so that all the things that are conserved are still conserved in the way that we're describing them. And that will not be true if we ignore these things. We have to keep careful track of these things. And people had been sloppy about that. And we learned how to be very precise and careful about it.
And once you're being precise, you can actually you can actually answer this kind of very problematic thing that Hawking suggested, that black holes destroy information.
Well, what we showed is that there's an error in the argument that all black holes are the same, because they hadn't kept track of these very subtle things. And whether or not this is the key error in the argument remains to be seen, or whether this is a technical point.
Yes, but it is an error.
It is an error.
And Hawking obviously agreed with it.
Hawking agreed with it, and he was sure that this was a
critical error.
That this was the critical error, and that understanding this would get us the whole story, and that could well be.
What was it like working with Stephen Hawking on this particular problem? Because it's kind of a whole journey, right?
Well, I love the guy. He's so passionate about physics. He just, yeah, his oneness with the problem it's.
So his mind is all occupied by the world that's
Yeah.
and
let me tell you, there's a lot of other things with his illness and with his celebrity, and
yeah,
a lot of other things.
A lot of distractions pulling at his mind. He's still there. He's still right there.
That's right. I remember him turning down tea with Lady Gaga so we could spend another hour on her paper.
That, my friends, is dedication. What did you learn about physics? What did you learn about life from having worked with Stephen Hawking?
Well, he was one of my great teachers. Of course, he's older than me, and I was reading his textbooks in graduate school, and I learned a lot about relativity from him. I learned about passion for a problem. I learned about not caring what other people think. Physics is an interesting culture. Even if you make a great discovery, like Hawking did, people don't believe everything you say.
Mm-hmm.
In fact, people love to disagree. It's a culture that cherishes disagreement, and so he kept ahead with what he believed in, and sometimes he was right, and sometimes he was wrong.
Do you feel pressure from the community? So, for example, with string theory, it was very popular for a time. There's a bit of criticism, or it's less popular now. Do you feel the forces of the community as it moves in and out of different fields, or do you try to stay, like, how difficult is it to stay intellectually and mathematically independent from the community?
Personally, I'm lucky. I'm well equipped for that. When I started out in graduate school, the problem of quantum gravity was not considered interesting.
You still did it anyway.
I still did it anyway. I'm a little bit of a contrarian, I guess, sure. And I think that has served me well. People are always sort of disagreeing with me, and they're usually right, but I'm right enough.
And like you said, the contradiction ultimately paves the path of discovery.
Yeah.
Let me ask you, just on this tension, we've been dancing between physics and mathematics. What to you is an interesting line you can draw between the two? You have done some very complicated mathematics in your life to explore the laws of nature. What's the difference between physics and mathematics to you?
Well, I love math. I think my first love is physics, and the math that I've done, I've done because it was needed
in service of physics.
In service of physics, but then, of course, in the heat of it, it has its own appeal, and
in the heat of it, I like it. Sure,
it has its own appeal, and I certainly enjoyed it. And ultimately, I would like to think, I wouldn't say I believe, but I would like to think that there's no difference between physics and mathematics, that all mathematics is realized in the physical world, and all physics has a firm mathematical basis, that they're really the same thing. I mean, why would there be math that had no physical manifestation? It seems a little odd, right? You have two kinds of math, some that are relevant to the real world.
Well, they don't have to be contradictory, but you can have can't you not have mathematical objects that are not at all connected to the physical world? So, I mean, this is to the question of, is math discovered or invented? So to you, math is discovered,
Yeah.
and there's a deep linkage between the two.
Yeah.
Do you find it at all compelling, these ideas, like something like Max Tegmark, where our universe is actually fundamentally a mathematical object? That our universe is mathematical, fundamentally mathematical in nature.
My expertise as a physicist doesn't add anything to that. It's not really,
Yeah.
physics is, I was once very interested in philosophy and, physics. I like questions that can be answered, that it's not obvious what the answer is, and that you can find an answer to the question and everybody will agree what the answer is, and that there's an algorithm for getting there. Not that these other questions aren't interesting, and they don't somehow have a way of presenting themselves. But to me, the interesting thing is motion in what we know, is learning more and understanding things that we didn't understand before, things that seemed totally confusing, having them seem obvious. That's wonderful. So I think those questions are there. I mean, I would even go further, the whole multiverse. I don't think there's too much concrete we're ever going to be able to say about it.
This is fascinating because you spend so much time in string theory, which is devoid from a connection to the physical world for a long time. Like not devoid, but it travels in a mathematical world that seems to be beautiful and consistent, and seems to indicate that it could be a good model of the laws of nature. But it's still traveling independently because it's very difficult to experimentally verify.
Well,
but there's a promise laden in it, in the same way multiverse, or you can have a lot of kind of very far out there questions where your gut and instinct and intuition says that maybe in 50, 100, 200 years, you'll be able to actually have strong experimental validation, right?
I think that with string theory, I don't think it's likely that we could measure it, but we could get lucky. In other words, just to take an example, about 10 or 20 years ago, it was thought that they had seen a string in the sky, and that it was seen by, doubled stars that were gravitationally lensed around the gravitational field produced by some long string. There was a line of double lensed. Now the signal went away, okay? But people were hoping that they'd seen a string, and it could be a fundamental string that had somehow gotten stretched, and that would be some evidence for string theory. Mm-hmm. There was also bicep 2, which the experiment was wrong, but it could have happened. It could have happened that we got lucky, and this experiment was able to make direct measurements. Certainly would have been measurements of quantum gravity, if not string theory. So it's a very logical possibility that we could get experimental evidence from string. That is a very different thing than saying, do this experiment, here's $1 billion, and after you do it, we'll know whether or not strings are real. But I think it's a crucial difference. It's measurable in principle, and we don't see how to get from here to there. If we see how to get from here to there, in my eyes, it's boring, right? Mm-hmm. So when I was a graduate student, they knew how to measure the Higgs boson. It took 40 years, but they did it. Not to say that stuff is boring. I don't want to say that stuff is boring. Yeah. But when Magellan set out, he didn't know he could get around the world. There was no map. Yeah. So I don't know how we're going to connect in a concrete way all these ideas of string theory to the real world. And When I started out in graduate school, I said, what is the most interesting problem that there might be, the deepest, most interesting problem that there might be progress on in 60 years? And I think it could be, that, in another 30 years, that maybe we'll learn that we have understood how black holes store information. That doesn't seem wild. That we're able to abstract what we learned from string theory and show that it's operative, and I mean, the Bose-Einstein condensate they did, when Bose and Einstein predicted it, when was that? The 30s, maybe early 30s. There were 20 orders of magnitude that were needed in order to measure it, and they did 50 years later. So, and you couldn't have guessed how that had happened, how they could have gotten that. And it could happen that I don't think we're going to see the heterotic string spectrum at an accelerator, but it could be that things come around and in an interesting way, and somehow it comes together. And the fact that we can't see to the end isn't a reason not to do it. We're just, what did they do when they were trying to find the Pacific, right? They took every route. They just tried everything. And that's what we're doing. And I'm taking the one that my nose tells me is the best, and other people are taking other ones. And that's good, because we need every person taking every route. And, if somebody on another route finds something that looks really promising, I'm going to make a portage over the mountain and get on their stream, So the fact that you don't see the experiment now isn't, to me, a reason to give up on what I view as the most fundamental paradox in 21st century physics.
Absolutely. You can see that it's possible. You just don't know the way. But that's what I mean, why some of the philosophical questions could be formulated in a way that's explorable scientifically. So some of the stuff we've talked about, but, for example, this topic that's become more okay to talk about, which is the topic of consciousness. To me as an artificial intelligence person, that's a very practically interesting topic. But there's also philosophers. Sean Carroll loves to argue against them, but there's some philosophers that are panpsychists.
I'm not against philosophers. It's just not as fun.
It's not as fun. All right. But they start a little flame of a fire going, that some of those flames, I think, eventually become physics. So eventually become something that we can really, having them around is really important, because you'll discover something by modeling and exploring black holes that's really weird. And having these ideas around, like the ideas of panpsychists that consciousness could be a fundamental force of nature. Just even having that crazy idea swimming around in the background could really spark something where that you were missing something completely.
Mm.
And it's just, that's where the philosophy done right, I think, is very useful. That's where even these thought experiments, which is very fun in the sort of the tech sci-fi world, that we live in a simulation, that, taking a perspective of the universe as a computer, as a computational system that processes information, which is a pretty intuitive notion, but you can just even reframing it that way for yourself could really open up some different way of thinking.
Could be.
And then you have, I don't know if you're familiar with Stephen Wolfram's work of cellular automata and complexity.
Yeah. I did a podcast with Stephen.
With Stephen? That's awesome. I mean, to me, forget physics, forget all that. Cellular automata make no sense. They're so beautiful. They're so, that from simple really rules, incredible. You can create complexity. I just don't think, he wrote a book, A New Kind of Science, basically hinting at which a lot of people have hinted at, is like we don't have a good way to talk about these objects. We can't figure out what is happening here. These
Yeah.
trivial rules can create incredible complexity.
He's totally right about that. Yeah.
And physicists, I guess, don't know what to do with that. Don't know what to do with cellular automata, because you can describe the simple rules that govern the system, but
Right.
how complexity can emerge, like incredible complexity.
Yeah. Of course, Wolfram's version of that is that physicists will never be able to describe it.
Right. Yeah, exactly. He tries to prove that it's impossible. What do you make of that? What do you make about the tension of being a physicist and potentially not being able to? It's like Freud or somebody that maybe Sigmund Freud, that maybe you'll never be able to actually describe the human psyche. Is that a possibility for you? That you will never be able to get to the core fundamental description of the laws of nature?
Yeah. So I had this conversation with Weinberg.
Yeah. How did it go?
So Weinberg has this book called Dreams of a Final Theory.
Yeah.
And I had this conversation with him. I said, why do you think there's ever going to be a final theory? Why should there ever be a final theory? I mean, what does that mean? The physics department's shut down. We've solved everything. And, what is it? Doesn't it seem that every time we answer some old questions, we'll just find new ones, and that it will just keep going on forever and ever? And he said, well, that's what they used to say about the Nile. They were never going to find the end. Then one day they found it.
Yeah.
So I don't know. String theory doesn't look like a candidate to me for a final theory.
As it stands now, it doesn't get to the bottom of the well, to the sides, into the whole.
Yeah, it seems to me that even if we kind of solved it and we've did experiments, there still would be more questions, like why are there 4 dimensions instead of 6? It doesn't seem to have anything that in it that would explain that. You can always hope, that there's something that we don't know about string theory that will explain it, but it still doesn't look like it's going to answer every question. And why is there 1 time, not 2? Why is there? It doesn't seem like it's. I don't even know what it would mean to answer every question.
Well, to answer every question, obviously. So when you refer to the theory of everything, you'll be able to have if it exists, it would be a theory that allows you to predict precisely the behavior of objects in the universe and their movement, right? What about them? Their movement.
Yeah.
Like precisely, no matter the object.
Right, that's true. So that would be a really interesting state of affairs if we could predict everything, but not necessarily understand everything. So, for example, let's just forget about gravity. I mean, we're not too far from that situation. If we forget about gravity, the standard model, in principle, given a big enough computer, predicts almost everything. But if you look at the standard model, it's kind of a laundry list with neutrino masses and all that stuff. There are hundreds of free parameters. Where do they come from? Is there an organizing principle? Is there some further unification?
Sure.
So being able to predict everything is not the only goal that physicists have.
Mm-hmm. So on the way to trying to predict, you're trying to understand. That's actually probably the goal, is to understand.
Yeah. But right, we're more interested in understanding than actually doing the predictions. But the predictions are more focusing on how to make predictions is a good way to improve your understanding, because you've understood it if you can do the predictions.
Yeah, one of the interesting things that might come to a head with is artificial intelligence. There's an increasing use of AI in physics. We might live in a world where AI would be able to predict perfectly what's happening, and so that will as physicists, you'll have to come to to the fact that you're actually not that interested in prediction. I mean, it's very useful, but you're interested in really understanding the deep laws of nature versus a perfect
Yeah,
predictor.
yeah.
Like you want to play
But even
chess.
within AI,
Yeah.
AI people are trying to understand what it is that the AI bots have learned in order to produce whatever they produce.
For sure, but you still don't understand deeply, especially because they're getting, especially language models. If you're paying attention, the systems that are able to generate text, they're able to have conversations. ChatGPT is the recent manifestation of that. They just seem to know everything. They're trained on the internet. They
Yeah.
seem to be very, very good at something that looks like reasoning. They're able to generate. You can ask them questions. They can answer questions. It just feels like this thing is intelligent, right? And I could just see that being possible with physics. You ask any kind of physical question, and they'll be able to very precise about a particular star system or a particular black hole. It'll say, "Well, these are the numbers." It'll perfectly predict, and then sure you can understand how the neural network is the architecture is structured. Actually, for most of them now, they're very simple. You can understand what data is trained on. Huge amount of data. You're giving it a huge amount of data from a very nice telescope or something. And then, but it seems to predict everything perfectly. You know how a banana falls when you throw it. Everything is perfectly predicted. You still don't have a deep understanding of what governs the whole thing. Um,
Yeah.
and maybe you can ask it a question. It'll be some kind of Hitchhiker's Guide to the Galaxy type answer. It's a funny world we live in. Of course, it's also possible that there's no such deep, simple governing laws of nature behind the whole thing. I mean, there's something in us humans
It's possible.
that wants it there to be,
Yeah.
but doesn't have to be, right?
Right.
I do. Where do you, again, you're betting you already bet the farm, but if you were to have a second farm, do you think there is a theory of everything that we might get at? So simple laws that govern the whole thing.
I don't, honestly, I don't know, but I'm pretty confident that if there is, we won't get to it in my lifetime. I don't think we're near it.
But doesn't it feel like like the fact that we have the laws we do, they're relatively simple already. That's kind of incredible. It's just there seems to be simple laws that govern things, right?
By a theory of everything, you mean a theory of everything, an algorithm to predict everything,
But a simple algorithm.
a relatively simple algorithm to predict everything. So for me, it would be a sad day if we arrived at that without answering some deeper questions.
Sure, of course, it definitely is. But the question, yes, but one of the questions before we arrive there, we can ask: does such a destination even exist? So, because the asking the question and the possible answers and the process of trying to answer that question is in itself super interesting. Because
Yeah.
is it even possible to get there where there's an E equals MC squared type of there's a function. Okay, you can have many parameters, but a finite number parameter function that can predict a lot of things about our universe.
Well, okay, but just to sort of throw one thing in order to answer every question, we would need a theory of the origin of the universe.
Right.
And that is a huge task, right? So, and the fact that the universe seems to have a beginning defies everything we know and love, right? Because we one of the basic principles of physics is determinism, that the past follows from the present follows from the past, the future follows from the present, so on. But if you have the origin of the universe, if you have a big bang, that means before that there was nothing. And you can't have a theory in which something follows from nothing. So somehow,
Sounds like you don't like singularities.
well,
I thought for somebody that works with black holes, you would get used to them by now.
no, I like this because it's so hard to understand. I like it because it's hard to understand, but but it's really challenging us.
Yes.
It's not I don't think we're close to solving that problem.
So even
And string theory has basically had nothing. There's been almost nothing interesting said about that in the last many decades.
so string theory hasn't really looked at the Big Bang. It hasn't really tried to get to the origin.
Not successfully. Not in there aren't compelling papers that lots of people have read that people have taken it up and tried to go at it, but there aren't compelling. String theory doesn't seem to have a trick that helps us with that puzzle.
Do you think we'll be able to sneak up to the origin of the universe, like reverse engineer it from experimental, from theoretical perspective? Like, okay, if we can, what would be the trajectory?
You've already gotten yourself in trouble, you see, because you used the word reverse engineer.
Sure.
So if you're going to reverse engineer, that means, you forward engineering means that you take the present and determine the future. Reverse engineering means that you take the present and determine the past.
Yeah.
But
estimate the past. But yes, sure.
But if the past was nothing, how are you ever going to reverse engineer to nothing? Well, that's hard to do.
Run up against the nothing, right? Until have mathematical models that break down nicely to where you can actually start to infer things. Do you think?
Let's work on it.
No, but do you think that
it could maybe, but it is. People have tried to do things like that,
yeah,
but
have not succeeded.
It's not something that we're getting A pluses in.
Sure. Let's pretend we live in a world where in 100 years we have an answer to that.
Yeah.
What would that answer look like? What department is that from? What fields led us there? What not what fields, what set of ideas in theoretical physics? Is it experimental? Is it theoretical? Like, what can you imagine could have possibly lead us there? Is it through gravitational waves and some kind of observations there? Is it investigation of black holes? Is it simulation of universes? Is it maybe we start creating black holes somehow? I don't know. Maybe some kind of high energy physics type of experiments.
Well, I have some late night ideas about that aren't really ready for prime time.
Okay, sure, but you have some ideas. Okay.
Yeah, but and many people do. It could be that some of the advances in quantum information theory are important in that they kind of go beyond taking quantum systems and just replicating themselves, but combining them with others.
Do you think, since you highlighted the issue with time and the origin of the universe, do you think time is fundamental or emergent?
I think ultimately it has to be emergent.
Yeah, what does it mean for time to be emergent?
Well, let's review what it means for space to be emergent.
Yes.
What it means for space to be emergent is that you have a holographic plate and you shine some light that's moving in space, and it produces an image which contains an extra spatial dimension, and time just goes along for the ride. So what we'd like to do, and indeed there is some rather concrete work in this direction, though again, I would say even within our stringing community, we're not getting A pluses on these efforts. But what we'd like to do is to see examples in which the extra space-time dimension is time. In other words, usually what we understand very well mathematically is how to take systems in some number of space-time dimensions and rewrite them as a plate in fewer space dimensions. What we'd like to do is to take systems with one time and some number of space dimensions and to rewrite them as a system that had only space dimensions in it, had no time evolution. And there's some fairly concrete ideas about how to do that, but they're not, universally accepted even within the stringy community.
But isn't it wild to you
Yes.
for to be emergent? How do we
Yes.
intuit these kinds of ideas as human beings for whom space and time seems as fundamental as
Well,
apples and
they're
oranges?
both illusions.
Okay.
They're both illusions, even time.
You co-authored a paper titled Photon Rings Around Warped Black Holes. First of all, whoever writes your paper titles, you like the soft hair and the term black hole and the Big Bang, you're very good at coming up with titles yourself. Anyway, you co-authored a paper titled Photon Rings Around Warped Black Holes. In it, you write, quote, recent work has identified a number of emergent symmetries related to the intricate self-similar structure of the photon ring. So what are photon rings? What are some interesting characteristics of a photon ring?
So that was a paper with Dan Kapitz and Alex Lipsaska that just came out. And this paper is kind of a wonderful example of what happens when you start to talk to people who are, way out of your comfort zone of know different stuff and look at the world a different way. And some 2 or 3 years ago, I'm part of this the Black Hole Initiative. I'm also part of this Event Horizon Telescope collaboration that took the famous, though I had nothing to do with the experiment, but that took the famous picture of the donut of M87, and through conversations with them, which started out in an effort to understand the image that they'd seen. So it's a great thing for somebody like me, a theoretical physicist, seemingly lost in stringland, to be presented with an actual picture of a black hole
and
to be asked, what can we learn from this?
Yeah.
So, with some help from, Michael Johnson and Alex Lipsaska, and a bunch of other people at the Event Horizon Collaboration, we came up with a fantastic, beautiful answer using Einstein's theory that is both shaping the future of it is shaping the future of improved black hole photographs. What do you want to concentrate on in the photograph? You just point it at the sky and click? No, you don't do that. You optimize for various features. And it's both shaping that, and in the process of talking to them and thinking about how light behaves around a black hole, black holes just have so many magic tricks and they do so many weird things. And the photon ring is among the weirdest of them. We understood this photon ring, and in the process of this, we said, hey, this photon ring has got to be telling us something about the puzzle of where the holographic plate is outside of an ordinary astrophysical black hole. I mean, we nailed it for the stringy black holes, but they have a somewhat different character.
What's a stringy black hole? The black holes that describe us, the string theory?
Black holes that are contained in string theory,
Yes,
and they have different structure in them.
Sure. Well, but actually, can we step back? So what was the light in the image taken in 2019?
Okay.
Well, not taken in 2019, presented in 2019.
So here's the puzzle. What they really saw, so the black holes tend to gather stuff that swirls around it.
Yeah.
And they don't know what that stuff is made of. They don't know what its temperature is. They don't know what kind of magnetic fields there are around there. So the form of the image has a lot of unknowns in it, that it's dependent on many other things other than the geometry of the black hole.
Sure.
So most of what you're learning is about the stuff. Now, the stuff, the swirling stuff, the hot swirling stuff is interesting as hell, but it's not as interesting as the black hole, which are the most, in my view, the most interesting things in the universe. So you don't want to just learn about the stuff. You want to learn about the black hole that is swirling around.
So at the very first step, at the very primitive level, this is just a big leap for human civilization to be able to see a black hole, and the way you can see it is because there's stuff around it.
Yeah.
But you don't get to learn much about the black hole. You get to learn more about the stuff just from the image.
Yeah.
Okay.
But you're not going to learn about the details before you've even seen it.
Because there's too many parameters, there's too many variables that govern the stuff.
Yeah. So then we found a very wonderful way to learn about the black hole. And here's how it works. A black hole is a mirror. And the way it's a mirror is if light, a photon, bounces off your face towards the black hole, and it goes straight to the black hole, just falls in, you never see it again.
Mm-hmm.
But if it just misses the black hole, it'll swing around the back and come back to you.
Yeah.
And you see yourself from the photon that went around the back of the black hole. But not only can that happen, the black hole, the photon can swing around twice and come back. So you actually see an infinite number of copies of yourself.
Like with a little bit of a delay.
With a little bit of a delay, right?
This is awesome.
Yeah. And in fact,
I mean, we're not used to an object that bends light like that,
yeah,
right?
Yeah.
So you're going to get some trippy, cool effects.
And in fact, one of my students has made a really awesome computer animation of this, which I'm going to show at a public lecture in a couple of weeks, where the audience will see infinitely many copies of themselves.
That's awesome.
Swirling around the black hole. So it's a black hole is like a hall of mirrors, like in a department store where you go and there's the three mirrors and you see infinitely many copies of yourself.
Yeah.
Think of the black hole as the mirror, and you go in there with your clothes. If you want to know about your clothes, you just look at the direct image. You're not learning anything about the configuration of mirrors. But the relation of the image you see in front of you to the one you see at the side and the next one and then so on depends only on the mirrors. It doesn't matter what clothes you're wearing. Mm-hmm. So you can go there 1,000 times wearing different clothes, but each time there will be the same relation between the subsequent images. And that is how we're going to learn about the black holes. We're going to take the stuff that is swirling around and we're going to tease out the subsequent images and look at their relation. And there's some very beautiful, really beautiful mathematics, which we were surprised to realize with the volumes and volumes of papers on black holes and their properties. This particular, because it was a physical question that had never been asked in exactly this way.
So basically, you're looking at the
relation between the subsequent images.
The relation, but those are ultimately formed by photons that are swirling around.
Photons that are orbiting. So the photon ring are the photons that orbit around
and beyond. So like orbit and lose orbit. Like
Yeah.
Like so. Wow. And that starts to give you, what can you possibly figure out mathematically about the black hole? The geometry of it, the spin
geometry,
of it?
The spin, and you can verify things behaving. We have never seen a region of space-time with such high curvature. I mean, the region around a black hole is crazy. It's not like in this room.
Right.
The curvature is everything,
You spend probably enough time with the math and the photons. Can you put yourself in that space? So we're like having a conversation in pretty peaceful, comfortable, flat space. Are you able to put yourself in a place around a black hole?
Yeah, I'm able to imagine that kind of thing. Yeah. So, for example, and actually, there's a wonderful movie, Interstellar,
Yeah.
and in that movie, Kip Thorne, of course, is a great theoretical physicist, experimental, who later won the Nobel Prize um, for LIGO. And that movie is very accurate scientifically. And there's some funny statements in there that of the 100 million people who saw that movie, there can't be more than 10 or 20 understood
Mm-hmm.
about why Matthew McConaughey is ejecting the trash in a certain direction in order to. and, but, for example, if I were a spinning black hole right here, if I was spinning fast enough, you wouldn't be able to stay still there. You'd have to be orbiting around like that, You'd have to have your microphone on a rotating
Yeah, but I wonder
basis.
what the experience is, what the actual experience, because I mean, space itself is curved.
Well, if space gets very curved, you get crushed. Your
Now,
body gets ripped apart because the forces are different on different parts of your body.
sure. Okay, so that would be.
But if it can be less curved so that the curvature is very noticeable, but you're not ripped apart.
The fact that this was just nonchalantly stated is just beautiful. Like two biological systems discussing which level of curvature is required to rip apart said biological system. Very well. So you propose in the paper that a photon ring of a warped black hole is indeed part of the black hole hologram. A photon ring of a warped black hole is indeed part of the black hole hologram. So what can you intuit about the hologram and the holographic plate from looking at the photon rings?
Well, this paper is exploring a new idea. It's not making a new discovery, so to speak. It's exploring an idea and the ins and outs of it and what might work and what might not. And this photon ring, somehow everybody always thought that the holographic plate sat at the horizon of the black hole.
Right.
And that the quantum system that describes the black hole is inside the horizon. And in fact, we think it's plausible, and we give some evidence in some soluble examples, in this case, in an example in one lower dimension where we can handle the equations better, that the quantum system that describes the black hole should correspond to a region of space-time which includes the photon ring. So it's bigger.
Hmm. So that would be the holographic plate. So
that would be the holographic plate.
All of that.
I mean,
Okay.
we didn't prove this. We put it out there. It hadn't really been considered previously. We put it out there, and it does seem more plausible than the idea that it sits literally at the horizon. And it is a big, outstanding problem of how you have a holographic reconstruction of black holes like M87.
Do you think there could be further experimental data that helps explore some of these ideas that you have for photon rings and holographic plates through imaging and through higher and higher resolution images, and also just more and more data?
I wish so, but I don't think so. But what I think already has happened and will continue to happen is that there are many different ways that theorists and observers can interact. The gold standard is the theorist makes a prediction, the observer measures it and confirms it, or the observer makes a discovery and the theorist explains it. But there's a lot less than that, which is really kind of the bread and butter of, those are dramatic moments when that happens, right? Those are once in a lifetime moments when that happens. But the bread and butter is more when it has already happened. They came to us and said, what is the interesting theoretical things we can understand in this swirl around the black hole? And we give an answer, and then that in turn jogged us to think about the holographic principle in the context of M87 a little bit differently. And so it's and in the same vein, it's useful to talk to the philosophers, and it's useful to talk to the mathematicians, and, a lot of, we just gotta, we don't know where we're going. We just gotta do everything.
Let me ask you another sort of philosophical type question, but not really, actually. It seems that thought experiments are used. So it's not just mathematics that makes progress in theoretical physics, but thought experiments do. They did for Einstein as well. They did for a lot of great physicists throughout history over the years. How's your ability to generate thought experiments, or just your intuition about some of these weird things like quantum mechanics or string theory or quantum gravity? Or, even general relativity. How's your intuition improved over the years? Have you been able to make progress?
The hard part in physics is most problems are either doable. Most problems that a theoretical calculation that a theoretical physicist would do, there's no end of problems whose answer is uninteresting. Can be solved, but the answer is uninteresting. There's also no end of problems that are very interesting, some of which you've asked me, but we don't have a clue how to solve them. And when first presented with a problem, almost every problem is one or the other. It's the jackpot when you find one that isn't one or the other. And
it seems like there's a gray area between the two, right? That's where you should be looking.
Well, I wouldn't describe it as a gray area. I would describe it as a knife edge.
So it's a very small area.
There isn't like a huge area with a sign, here lie problems that are doable, and people want to know the answer.
And that's, in some deep sense, that's where timing is everything with physics, with science, with discovery.
With timing. I mean, I think earlier in my career, I erred more on the side of problems that were not solvable.
The ambition of youth.
Yeah.
What made you fall in love with physics at first? If we can go back to the early days, you said black holes were there in the beginning, but what made you? Do you remember what really made you fall in love?
I wanted to reach nirvana, and I sort of realized that wasn't going to happen. And then after that, I wanted to know the meaning of life, and I realized I probably wasn't going to figure that out. And then I wanted to understand, justice and socialism and world things, and couldn't figure those out either. And
so the simplest, smaller and smaller problem until you arrive at black holes.
And then, I mean, most of this I'm talking about adolescence, but it was the biggest problem that I thought that there was a prospect of, but not 100%, and I was definitely ready to spend my life in the wilderness knocking my head against the wall, but I haven't had to. I haven't solved them, but I've said enough interesting things that you're interviewing me. So I'm not in the wilderness, but yeah. So
do you remember the early days? Do Do you feel nostalgic when you think back to the ideas, the circumstances that led you down the path towards black holes, towards theoretical physics, towards the tools of physics, towards this really fascinating world of theoretical physics?
Well, I wouldn't add nostalgia to it because it's not like you know, a summer in Italy or something. It's like there's results that are there that
Sure.
that that people are, and that's what's so gratifying. I mean, of course, one's name disappears from these things, unless you're Einstein or Newton or something. People are not going to remember my name in 50 years.
Well, no, basically every name will be forgotten in hundreds of years. Yeah.
Yeah.
Are
And
you able to, by the way, um, love the exploration of ideas themselves without the names, the
yeah,
recognition, the fame, the
that's what I'm
awards?
saying. So I have not. I hope someday, but I have not. There are some experiments now to verify some of my predictions about properties of gravity and so on. But I have not, like, most of what I've done is in the it could happen still. It's still a logical possibility that everything having to do with string theory and I mean, as we mentioned, I'm betting the farm that it's not, but it is indeed a logical possibility that people always say, "Can you believe Lex Fridman interviewed Elon Musk and Kanye West, and then he interviewed Strominger, who was on this working on this theory that just
Yeah.
completely went into the toilet."
I'm gonna make. I'm gonna get with a wife I don't have. I'm gonna make a public statement. She'll be on stage. I'll say, "I'm really sorry. I made this giant mistake of platforming this wild-eyed physicist that believed for decades in the power of theoretical physics." Yes. No. Like you said.
So that could happen. It could happen. It could happen. It's in the, and of course, if that couldn't happen,
Yeah.
it wouldn't be real exploration, right?
Absolutely.
And but I do take a lot of satisfaction that some of the things I discovered are, at the minimum, mathematical truths, and they're still, so you don't have that sort of nostalgic feeling of it being something that was gone, and I'm still making discoveries now that I'm as excited about. We'll see if they hold the test of time, that stand the test of time that these other ones did, but that I'm as excited about as I was about those when I made them. I am easily excitable, as my friends will tell you.
Well, one interesting thing about you is
And I have been very excited about things which turned out to be completely wrong.
well, that's the excitement is a precondition for breakthroughs. But you're also somebody, like just like you said, you don't have a cynical view of the modern state of physics. So
No.
so there's a lot of people that glorify like the early days of string theory and that all the discoveries that were
Yeah,
made in the
people are
20s and so on.
always, yeah.
But you're saying like this to you uh might be one of, if not the most exciting times to be a theoretical physicist. Like when the alien civilizations 500 years from now that visit Earth will look back, they'll think the 21st century, some of the biggest discoveries ever were made in the
Yeah, I
21st
mean, when
century.
they have a measurement of string theory, the fun's over.
No, but
Then we have to go on to something new.
no, there's going to be the fun is over. Oh man, but there is an end to the Nile, right? I mean,
Is there? Who told you?
some some Weinberg guy. Uh, let me ask you another trippy out there question. Again, perhaps unanswerable from a physics perspective, but do you wonder about um, alien civilizations? Do you wonder about other intelligent beings out there making up their own math and physics, trying to figure out the world? Do you think they're out there?
it is hard to understand why there would, given that there's so many planets, and of course there's Drake's formula, and we don't exactly know but I mean, I think Fermi's paradox that, is a real paradox, and I I think there probably are, and I think it's very exciting that you know we might find some. It's a logical possibility that we could learn about it.
I mean, to me, it's super interesting to think about aliens from a perspective of physics, because so any intelligent civilization is going to be contending with the ideas, just trying to understand the world around it. So I think that I think that the universe is filled with alien civilizations. So they all have their physicists, right? They're all trying to understand the world around them. And it's just interesting to me to imagine all these different perspectives, all these different Einsteins.
Yeah.
Like trying to make sense of like,
Though they might be more different than we think. They
why,
might be different in a way that we haven't even thought of.
like smarter or different?
Just different, something that we're not even able to describe now. We
Yeah,
just haven't thought of it,
Yeah. Yeah, this is a really frustrating thing when we think from me as an AI person, you start to think about what is intelligence, what is consciousness, and you start to sometimes, again, night evening thoughts is how little we understand, how narrow our thinking is about these concepts.
Yeah.
That it could be intelligence, could be something, could be intelligent and be very different, intelligent in a very different way that we won't be able to detect because we're not keeping an open enough mind. And that's kind of sad because to me, there's also just a strong possibility that aliens or something like alien intelligence or some fascinating, beautiful physical phenomena are all around us. And we're too dumb to see it for now. We're too close-minded to see it. There's something we're just deeply missing, whether it's like fundamental limitations of our cognitive abilities or just because our tools are too primitive right now. Or like the way it's like you said, like the ideas seem trivial once you figured it all out, looking back.
Yeah.
But that kind of makes me sad because there could be so much beauty in the world we're not seeing because we're too dumb.
There surely is.
And that's, I guess, the process of science and physics is to keep exploring, to keep exploring, to find the thing that will, in a century, seem obvious.
Well, something we know for sure. I mean, the brain we don't really understand, and that's got to be some fabulously beautiful story that
I'm hoping some of that story will be written through the process of trying to build a brain. So the process of engineering intelligence, not just the neuroscience perspective of just looking at the brain, but trying to create it. But yeah, that story hasn't been written almost at all, or just the early days of figuring that one out. But see, like you said, that math is discovered. So aliens should at least have the same math as us, right?
I think so.
Maybe different symbols.
Oh, well, they might have discovered it differently. And they might have had a different idea of what a proof is.
Sure. Yeah. We're very like black and white with the proof thing.
Yeah.
Maybe they're looser.
Right. Well, so you can know something is true. First of all, you never know something is true with 100% uncertainty. I mean, you might have had a blackout it's never 100%, right? You might have had a momentary lapse of consciousness. It's a key step in the proof and nobody read it and whatever. Okay, so you never know for sure. But you can have a preponderance of evidence, which makes it. And preponderance of evidence is not accepted very much in mathematics. And that was sort of how, the famous Ramanujan work. He worked. He had formulas which he guessed at, and then he gathered a preponderance of evidence that he was sure they were true. And
Yeah.
so there might be, or something completely different. They might function in a very different way.
Let me ask you kind of a heavy question for a physicist, but one on nuclear weapons. Just in general, what do you think about nuclear weapons where, like philosophical level, where brilliant physicists and brilliant engineering leads to thing that can destroy human civilization? Sort of like some of the ideas that you're working on have power when engineered into machines, into systems. Is there some aspect of
Well,
you that
first of
worries
all,
about
I
that?
don't know what the brilliant had to do with it because, of course, Oppenheimer and all that. Okay, they did it really fast, but if you didn't have Oppenheimer,
Yeah.
I mean, would all have happened anyway? It had a reality of its own. The possibility of making a nuclear didn't depend on the fact that the physicists who built it were brilliant. Maybe that sped it up by a year or 2 years, but by now we'd have nuclear weapons. It's something that,
So the ideas have momentum and that they're
yeah,
unstoppable.
right. The possibility of making nuclear weapons was discovered. Right. It was there before.
Sure.
We didn't. It's not like somebody made it. Right. Um, Without Picasso, there would never have been a Guernica, but without Oppenheimer, there would surely have still been an atom bomb.
But timing matters, right? Timing is
But,
very important. There's a
but
guy
of
with a
course, of course, of
mustache I
course,
got to
of
tell you
course,
about.
of course, the timing mattered. The timing mattered there. But yeah, okay. I mean, you could try to make a case for stopping.
No. It's the case of carrying the burden of the responsibility of the power of ideas when manifested into systems. So it's not a game.
Yeah,
It's not just a game of fun mathematics. Just same with artificial intelligence. You have this, a lot of people in AI,
yeah,
it's a lot of people in the AI community. It's a fascinating, fun puzzle. How to make systems more and more intelligent. How to, you have a bunch of benchmarks. You try to make them perform better and better and better, and all of a sudden, you have a system that's able to outsmart people. It's now able to be used in geopolitics. It's able to create super intelligent bots that are able to, at scale, control the belief of a population of people. And now you can have world wars. You can have a lot of really risky
yeah. They're
instabilities that created.
incredible. They really are incredible.
And so, just like there's some responsibility. This is not sort of. It's a beauty and a power and a terror to these ideas.
Yeah. At that moment, it was certainly a question for Oppenheimer and everybody who participated in that. What is the responsible way to serve society when you're sort of accidentally in this position of being at the forefront of a development that has a huge impact on society? I don't see my work a likelihood of having a huge impact on the
Interesting.
development of society itself. But if I were you,
Oh, I love this.
working on AI,
Yeah.
I think that there is a possibility there, and that it is, as a responsible scientist, that it's really not a good thing to say, I'm just the scientist here and I'm figuring out what's possible, because you're in a role where you have more of a podium to influence things than other people, and it's your responsibility as a citizen of the planet, or let me phrase it a little less shouldy. It's, you have an opportunity
Yeah. Sure.
as a citizen of the planet to make the world a better place, which it would be sad to bypass.
Yeah, it's a nice world we got going. It'd be nice to keep it going for a little bit longer. Andrew, I'm really honored that you sit down with me. This is thank you for your work. Thank you
Well,
for
it was a really great conversation. I really enjoyed it. You really covered a lot. I can't believe you're able to discuss at this level on so many different topics. So it's a pleasure.
It was super fun. Thank you. Thanks for listening to this conversation with Andrew Strominger. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Werner Heisenberg. Not only is the universe stranger than we think, it is stranger than we can think. Thank you for listening, and hope to see you next time.